Hi, in this video, I'm going to talk about one of the most important terms in quality improvement, which is Six Sigma. I'm sure you have heard of it before. I'm going to explain what it is and why it's important. So CTQ stands for critical to quality. Each product has a number of CTQs, critical to quality characteristics. Each one of those, usually, if we measure them, has a distribution. Let's say it's a normal distribution with, and let's assume that its mean is the target value that we want it to be, and it also has some standard deviation. So we usually want to compare the distribution of a CTQ with specifications. The specifications are expressed in terms of lower specification limit and upper specification limit, LSL and USL. The difference between these distributions that you see in the center and those two lines is that those vertical lines are given to us by the customer or by the design or from design or engineers. But that distribution in the center is what we actually are producing. And we want to see, and whatever is outside of those vertical lines is basically waste or defects because they don't meet the specifications. Let's look at an example. For example, let's say we're producing this toy, all right? And one of the CTQs for this toy is the diameter of each wheel, right? So that diameter, which is the length of that diameter, it's in millimeters. For example, if you produce thousands of those, millions of those, and then you actually measure the diameter of the wheel and put it on a histogram, it will have a distribution, right? It will have a mean and a standard deviation. Let's say that blue distribution here is the distribution of the diameter of the wheel that we're producing. And let's say the specifications are the target is 20 millimeters, which is a little smaller than an inch, and we don't want it to be larger than 20.30 millimeters, and we don't want it to be smaller than 19.70. Otherwise, it will wobble, right, when you're driving it or the kid is driving it. Okay, so those lines, therefore, those vertical lines are going to be 19.70 all the way to 20.30. And we want to see what where our distribution stands there. If the distance between the mean of our distribution and the USL or the LSL, if that distance is 3 sigma, then we would say that we are producing in 3 sigma. And in that case, 99.73% of the wheels that we're producing are actually within a specification. What does that mean? It means that we're producing here, and it means 99.73% are within the specifications, but 2,700 of the parts that we're producing, the wheels that we're producing per billion are defective. So ppm, parts per million, 2,700 will be defective, which means they will be out of the specifications. They will be either larger than 20.30 or smaller than 19.70. All right. So let's look at an example. Let's say I have a plant and I produce these wheels, and I actually measure a large sample of them, and I realized that the mean of diameter of those wheels that I'm producing is 20, which is great. It's just like the target. And then there is a 0.10 standard deviation. So 20 plus 3 times 10 is going to be actually my USL. So this distance is 3 sigma. 20, the target, plus 1, 2, 3 of these 0.10s is going to be 20.3, which is my USL. So I am producing in 99.73%. I'm producing in 3 sigma basically. Another example, let's say I have the same mean, but my standard deviation is smaller, which means I have lower variation in my production, which is good for quality, right? We learned that earlier. Then this distance between mean and USL is going to be is going to be 6 sigma, because this distance is 0.30 and you have to multiply 0.05 by 6 to get 0.30. So that distance is 6 sigma. In that case, our parts defective per million is only 0.002. It's not even 1 part, right? But here I made an assumption that what I'm producing actually has a mean equal to the target. All right, but that's not usually the case. Let's look at this example. Not this example, this concept basically, which says in practice, your mean, the mean of your distribution, this guy in the middle, that's going to shift a little bit to the right or to the left, and we want to, for example, it won't be actually 20. It won't be exactly 20, right? It's going to be 20 point something, the mean, right? And we want to express that shift from the target in terms of a multiple of the sigma of the distribution. So we would say 1.5 target plus minus 1.5 of the sigma. So if my sigma is 0.05, if we multiply that by 1.5, or if it's if it's 0.10, then 0.10 times 1.5 is going to be 15, right? So for this distribution, the sigma is actually going to go up to the mean is going to go up to 20.15, and it can go down to 19.85. All right, and we use this formula because the lower the variation, the lower that shift is going to be, right? The lower that shift is likely to happen. So for this 3 sigma production that we had, the first example, you can see that if we consider that shift also, then our parts per million for 3 sigma is going to be much more than what we had. It used to be 2,700. Now it's 66,810 parts defective per million. But for 6 sigma, which means if your sigma is just half of that, 0.05, even with that shift, you're still going to have only 3.4 parts defective per million, which is a very small number. Why is this important? So this thing that we saw here, this number 3.5, is only for one CTQ, which means we have other CTQs. For example, for this toy, each one of these components, each one of these parts here has its own CTQ, right? And if we have 10 of these, for example, each one of them that's out of a specification leads to a defective product, right? The product can be defective because of the wheel diameter or because of the shaft diameter or any of those things. Let's say this toy has 10 parts, right? And let's say they are all being produced in 3 sigma, which is actually good. 3 sigma is not bad. But if that's the case, we can see here that 99.73% are going to be good parts within the specifications. So the probability that all 10 are within the specifications, which means the entire product is conforms to the specification and it's not defective, that probability is 0.7631, which translates to 236,900 parts per million defective, which is a lot of defective parts. So that shows the significance of why it's so important to produce within Six Sigma. And so, in short, to summarize, Six Sigma is the distance between target and USL or LSL. And so the total distance when we're producing in Six Sigma is going to be 12 sigma, minus 6 sigma to all the way to plus 6 sigma, which will be 12 sigma. And also, please remember that this distribution represents our actual production, but these USL and LSL are given to us. Okay. All right. Let's see what's next.